Okay, so if we look at this, we write out the monohydrogen phosphate ion. Well, that's one hydrogen with the phosphate ion. Because we've added one hydrogen, we've reduced the charge on that ion by 1. So this is an acid in its own right, so it can produce a hydrogen and a phosphate ion. So you see that acids aren't always neutral compounds, and bases can be a charged compound too. We think of molecular bases, and we're going to see a chart of them in a little bit, but the conjugate base of a weak acid can also act as a base in its own right. So now we have Ka is equal to H plus times PO4 3 minus divided by HPO4 2 minus. So this is the first time we look at something that's not a neutral species as an acid. And it doesn't matter if it's neutral or if it's charged, it can still have acidic behavior. Now, if you felt uncomfortable with that because you didn't know the monohydrogen phosphate ion's formula, that's okay. You may not know the formula for a lot of things as we go forward in these examples, but I hope you know how to read a chart. So if you look on page 16-16 in your notes, here is a chart of weak acids. So hopefully you can read this chart. If it's got a word name, they're right here. The formulas are here. So if it's something you don't recognize, the chart will always be in your possession. You'll have the chart on a test. You'll have the chart on a quiz if needed. The chart's in your notes. It's in your textbook. So don't panic about that. Okay, now let's look at doing an actual problem similar to what we did in Chapter 15. The pH of 0.1 molar formic acid is 2.38 at 25 degrees C. Calculate the Ka and pKa for this acid. Well, we know that it is a weak acid because it's not one of the 7 strong, and it's on the list labeled weak acids. So that's how you know it's a weak acid. 2 clues, right? So now we can look at this and say, okay, here's our dissociation. And if you don't like this, it's always okay to say HA is in equilibrium with H plus and A minus using our generic. Just using the generic, then, Ka is equal to H plus times A minus divided by HA. So my goal here is to find Ka. So if I knew these 3 numbers, then I could find the Ka. And let's look at what I do know. I know the initial concentration of this acid before it dissociates, and I know the pH. What does pH represent here? What? It's the negative log of the hydrogen ion concentration, and it's the equilibrium hydrogen ion concentration. So, since I know the pH, I can find the hydrogen ion concentration. And then I could figure this out. So we'll start by calculating the hydrogen ion concentration from the pH that's provided. We know that the hydrogen ion concentration is 10 to the negative pH, so that's 10 to the negative 2.38, and that is equal to 4.2 times 10 to the negative 3rd molar at equilibrium. So now we go back to this ice chart that we developed in the earlier chapters. And when we look at this, we can say, okay, what do I know that I can fill in that chart? So we know the initial concentration of our acid, 0.1 molar. And we know the equilibrium concentration of the hydrogen ion, 0.0042 molar. So how do we use this information to figure out the rest of the equilibrium concentrations? Well, when we put the stuff in the beaker and it hasn't dissociated yet, what's the hydrogen ion concentration? 0. And what's the hydrogen, the HCO2 concentration? That should have a negative charge. That's a typo. Should be a charge. 0. So if I go from 0 to 0.0042, then this changed by 0.0042. This balanced equation is 1-to-1-to-1 stoichiometry. So this has to change by 0.0042 also. So at equilibrium, I have 0.0042 molar of the formate ion as well. Now, what's happening over here to the formic acid? It's decreasing by the same amount, right? Minus 0.0042. So at equilibrium, that's 0.096 molar. So now I have the equilibrium line, and I have all of the equilibrium concentrations, so I can find my Ka just like I did with any other equilibrium in Chapter 15. This is the same, only easier because it's all 1-to-1 stoichiometry. You don't have to worry about 2s and 3s and squaring and cubing things. I think that makes it easier. So we have Ka is equal to H plus times A minus divided by HA. Now we just plug in our equilibrium concentrations. 0.0042 molar for the hydrogen, 0.0042 molar for the formate ion, divided by the equilibrium concentration of the acid, 0.096 molar. That'll give us our Ka equal to 1.8 times 10 to the negative fourth. And that seems like a reasonable Ka for a weak acid. And if you look at this, it seems reasonable because we still have quite a bit of acid and really relatively very little H plus and A minus, only a small amount associated. So now we know Ka. How do we find pKa? pKa is minus the log of 1.8 times 10 to the negative fourth. So that's equal to 3.74, our pKa. So there's really nothing new here. The math is the same, the ice chart is the same, the chemistry is different. But it doesn't matter what the chemistry is once you start doing your calculations. And we're just taking that equilibrium line and we've used pH to find out some of that information. So go ahead, grab your whiteboards and do this next one in your groups.